Folds are amongst the most impressive geological structures, happening on all scales, from whole Arctic islands and mountain ranges like the Zagros of Iran, to microscopic folds in these slates. They're not just architectural and beautiful, but host important earth resources like gold veins and pods of sulfide hosted ores, and here in a salt mine in Sicily. So it's important to understand folds and folding processes. Many basic ideas on folds and folding were built from careful observations from outcrops like this. These are structures preserved at the famous geological site Loch Monar. And so I'm driving into the heart of Scotland's northwest Highlands. The journey takes me up a long private road, open to traffic if you check opening times, which leads up Strathfarra to the dam at the head of the valley. The reservoir is Loch Monar. The glaciated slabs along the shores of the loch provide exceptional exposures. And these used to be required stops on geological field excursions, but this type of rather fundamental geology has become a little unfashionable. So it's time to rejuvenate interest in these wonderful and accessible, almost roadside outcrops. In the mid-1950s, a geologist called John Ramsay did his PhD in the countryside around here, and he found these spectacular outcrops. John went on to become one of the most famous and influential structural geologists of the 20th century, writing a classic textbook that was required reading for generations of students. This is my copy. One of the first textbooks I bought as a student in Leeds, many years ago. Folding and fracturing of rocks set the agenda for structural research for many years. John spent most of his career after he published his landmark book in Zurich, working in the Alps, but always had a soft spot for his formative studies in Scotland. So let's follow in John's footsteps and explore these really stunning outcrops on the side of Loch Monar. To the uninitiated, it might seem surprising that rocks can deform like this. They can flow, and it doesn't mean that they were molten, though we'll see later that here at Loch Monar, tiny patches did melt. But no, under long periods and slow rates of deformation, rocks can flow and mimic the behaviour of viscous fluids in just the same way as, over years, glaciers of ice can flow. So, what are the rocks here? They're metamorphosed sedimentary rocks. Most are samites, that's metamorphosed quartzo-felspathic sandstones, and they're fairly uniform. But other parts are well banded, with former muddier shaly layers, semi-peelites. And some of the former muddy layers are well defined. Then, within the layers are quartz veins, generally near parallel to layering, with various thicknesses. So these are the materials that are folded, a nice mix that we can use to explore different behaviours during deformation. And there's a surprise in store at the end. So let's start by looking at the samites. They fold in a particular way. Each band mimics its neighbour, and across an outcrop, the folds tend to look rather like each other. The shapes very smoothly through the outcrop. These are called similar folds. And the examples at Loch Monar are classic. They feature in John's textbook. Ramsay also talks about folding of various orders based on their size. Small wavelengths embedded in larger, longer wavelengths ones. And Loch Monar has plenty of examples like this. As we go up one limb, across the hinge, and down the other limb. These small folds, second order for us, have particular asymmetries, defined by their own relative limb lengths. On this limb, symmetrical on the first order hinge zone, and on the other limb of the larger first order fold, and the asymmetry switches from large limb to large limb. It's a useful rule for mapping out major fold structures. So now let's look at the veins, which behave as relatively stiff layers within the metasediments. They fold by buckling. The theories and controls of buckling were developed by Maurice Biot and Hans Ramberg in the late 1950s and early 60s, and their ideas were developed by Ramsay in his textbook. Buckle folds are developed in layers that show strong contrast in their relative viscosity, and the fold wavelength reflects both this control and the thicknesses of the buckling layer. We can explore the thickness controls using the quartz veins at Loch Monar. So we've got a composite thick vein here, a little thin vein running on top, and we can see that the wavelength of the folding for the thick package of vein quite long compared to the really short wavelength behaviour in the thin vein. Let's zoom in. Here's the thick layer and the thin one. The spacing of the antiforms in the thick layer, essentially the fold wavelength, are these distances. And here are all the antiforms in the thin layer. This is a clear demonstration that the thin layer folds at a much shorter wavelength than its thicker counterpart. So layer thickness is controlling the fold geometry. But it gets more interesting in progressive deformation. Take this vein. It looks to be folding on a long wavelength across this view, and it's relatively thick. But let's look more closely. The vein is actually a closely packed fold train. So the vein is actually thin, but tight folds effectively thicken it up. And this new effective thickness means that as the deformation progressed, it folded on a longer wavelength. But as the veins are folding, what's going on in the surrounding metasediments? So take this quartz vein. It might look like it's just this thickness through here, but actually it's sort of concertinaed right up. And what's interesting is that the sammites down in here don't look like they're that folded. Now presumably the sammites shown the same amount of contraction then embedded together, but it's hardly folded at all. So the deformation in the sammite here presumably is rather like a soft pack of butter. It's just sort of thickened up by distributed strain. The buckling, well, that's experienced by the quartz vein. We can explore this in a simple animation. A yellow stiff layer, the quartz vein, encased in a lower viscosity matrix of sammite. So when compressed, the vein buckles, but the sammite doesn't, because the viscosity contrasts within it are insignificant. But think about the strain. The sammite still deforms, and if we add circle shapes and squash the thing, look how strained the sammite must be to match the deformation in the vein. And it's hard to detect this strain in the outcrop. So As discussed by John Ramsay following Biot and Ramberg, buckle folding is fundamentally controlled not just by layer thicknesses, but also the contrast in relative viscosity between layers. And the rocks at Loch Monar offer great illustrations of these dual controls. Because it's hard to quantify actual rock viscosities pertinent to the time of their deformation, geologists use the qualitative term competence to refer to these behaviours. High competence equals stiff layers with high relative viscosity. But what about layers which have lower viscosity relative to the rocks around them? They deform with strange scoopy cusped folds. This displays really nicely the impact of viscosity contrast on fold shape, where this darker band is behaving less competently, that's runnier if you like, than the stiffer, more competent samites on either side. And the incompetent material makes these pinched in fold shapes, whereas the more competent makes the bulbous shapes like this. And we can see that as we go along an individual fold, this one here, this lower samitic layer makes the bulbous shape, the fold continues along here, and then we got this really pinched in shape where the fold is cored by this darker, more polytic layer. So the ductility contrast is giving us different fold shapes. So this is a nice outcrop to put the first part of our story together. So we can see that the more polytic unit here has these more pinched in structures compared to the bulbous shapes in the samite on top here. We can see that the quartz veins show lots of buckling, even though the samite, well, the folds look a bit more gentle out in here. And we can also see that the thin quartz vein has got really intimate, short wavelength folding in here compared to the thick quartz vein, which has got much longer wavelength folding. So layer thickness controls on the fold geometries, competence contrast controlling the fold geometries. Before looking at other aspects of the folding here at Loch Monar, let's consider other aspects of the deformation. So there's a pretty clear trend, isn't there, in the structures running across the outcrop like this, implying major compression in this direction. And some of these structures get really tight. So in this outcrop here, the folding looks to be rather subdued, doesn't it? Although there's this really nice interfacial buckling between this slightly more polytic unit and the slightly more samitic either side. And the really neat thing about this is that these pinched in areas are where strain is more intense, and you can see it's defining a spaced, well, fabric through the outcrop like this, a parting that's spaced, tied to the fold shapes. Now this fabric through here has some other really remarkable features associated with it. There's a dominant trend to these structures, lots of tectonic shortening. But if you look closer, there are these little white patches and veins along highly flattened limbs of these similar folds. They're made of feldspar and quartz, leucosomes, patches of frozen melt. So the metamorphic conditions during deformation were sufficient to generate small amounts of melting in these metasediments. So this shows this behaviour really nicely, where we've got the samites and the polytic unit in here, nicely folded up, the trend of the folds coming through like this, quartz vein also folded. And as we trace these pinched in bits of the fold up into this material here, we can see these seams of leucosome, little frozen out melt patches on echelon through the outcrop. So little melt patches controlled by this really penetrative deformation.
The petrogenesis of these local melt patches and any associated migmatites has barely been researched. To my mind, this is a misstep in Highland geology because crustal melting gives important information for tectonics. But let's get back to the folding.
Well, there's really nice folds here at Loch Monar, but this place is really famous for fold interference patterns, because look at the complexity here. Let me just try and trace a bit of layering in the samite around. And then out. So it's really caught up. So there's, well, these two generations of fold here. And it's the interference between these fold phases, if you will, that create some of the really spectacular outcrop patterns here. So let's go around and look at some really classic examples.
Aha!
So these are classic examples of dome and basin fold interference, where we've got a set of folding happening like this and then refolding like this, generating essentially a pattern that looks like you've sliced through an egg carton. These really nice closed patterns in the layering in the samite. So let's sketch on the axial traces for these two generations of folding.
We can track one set running across like this. We can label these D1. And another set of folds running this way, D2. So we're implying a sequence of folding. Ramsay recognised other examples of these dome and basin patterns and interpreted them. But actually, for this particular pattern of refolding, the opposite sequence of events can explain it. But that's an aside, and it won't apply to other patterns of refolding we're about to see.
Okay, so now let's scout around and look for some other examples of different fold interference patterns. So this is another classic pattern. Nice fold closure here. Really tight fold. So let's trace its axial trace out. So it comes up here and it goes there, because I can see that layer closing around. And then it comes along here like this and then off like this, because that layer comes around. And then we can trace it all the way along here, all the way along and out, because we can see these layers come around like that. So let's just draw on that axial trace that I've just traced out.
Here's the layering in the samite and the axial trace running through. And it's refolded by an axis through here, a so-called crooked finger pattern.
So we've got an early fold that's been refolded through here. So a refolded fold structure.
It's another refolded fold geometry as recognised by John Ramsay. In his book, Ramsay charted out the different outcrop patterns resulting from superposed fold systems in various orientations. Many are illustrated by examples from Loch Monar. This is where it all comes from. Loch Monar may be famous for its refolded folds and for inspiring a young John Ramsay, but as we've seen, we can learn much more about how rocks fold in general. These rocks here have been seriously deformed, and there's more to learn about what these structures and their rather understudied metamorphic history tell of the tectonic evolution of northwest Scotland.
So that's a quick look at these fantastic outcrops at Loch Monar. It's a fold factory.